really happy to be able to take part in this session. So I want to talk about some work that Sendhil, Mullainathan, and I did and presented at EC in 2019. And the background for this work is the increasing way in which algorithms are being used for prediction problems and screening problems in so-called high-stakes social policy domains. And so obviously, we've seen a lot of this in the news recently, the way people are considering algorithms, for example, to help people evaluate job applicants, to help make admissions decisions to college or to graduate programs. The several decades that increasingly powerful algorithms have been used for making decisions about credit and lending. And even in the criminal justice system, where, for example, at a pretrial detention hearing, the law instructs a judge to make a prediction about whether a defendant is likely to return for their court appearance. And as a result, people have looked to quantitative tools to help in making that prediction that the law asks them to make. And so we have this pipeline in which we have people in the world getting mapped to some vector of features, passed through some decision maker, which is increasingly perhaps some human assisted by some algorithmic tools, making some prediction. Will this be a good job applicant? Will this person succeed in college? Will this person repay their loan? Will this person return for their court appearance? And whenever we have decisions like this, there is naturally a concern about bias coming into the process. So certainly the long history of research in the behavioral sciences on bias in human decision making, and then this recent and very active strand of work over the past 10 years on the risk of bias in algorithmic decision making. And in some sense, it's natural why there should be bias in these algorithmic decisions. The algorithm, of course, has no direct incentive to engage in bias. That's sort of by definition. The algorithm doesn't know who you are or why it's solving this problem. But if it's trained using the standard machine learning pipeline, then it's using features that come from your contact with human systems. It's matching you to a label that was defined by some human social structure. It's being trained on training data that was collected from society. And as a result, because there's bias in all of those things, it's natural that makes its way into the functions that are being learned. So what do we do about this? One natural approach is to try auditing the algorithms, to try looking at what they're doing. And we run into the problem that the algorithms typically are these very complicated black box models. And so people have begun to ask the question, to what extent can simplification of the algorithm help us potentially look for sources of bias, as well as many other concerns we might have about the algorithm. This, for example, is nicely encapsulated in this quote by Doshi, Villas, and Kim in one of the influential early surveys on interpretability of algorithms, to say that interpretability, the process of making the algorithm easier to understand, can assist potentially in qualitative understanding whether other desiderata such as fairness, privacy, reliability, robustness, and so forth are met. Now, the question that Sendhil and I asked was sort of a counterweight to the premise of this quote, which is, in the process of trying to achieve interpretability, a common heuristic, perhaps arguably the most common heuristic, is some form of simplification, right? To simplify the features that the algorithm is using, to simplify the functional form of the algorithm. And can this process of simplification potentially clash with our fairness goals? Why should this be, right? Why should there be any tension between the process of simplifying and the process of ensuring fairness? And this is where my co-author Sendhil's behavioral science and the intuition was very helpful, because in the behavioral sciences, in a very much a parallel, distinct strand of work, there's a long history of research into where do stereotypes come from, right? The stereotypes that we form about people. And two of the basic principles behind stereotype formation is that, one, they're particularly likely to arise in situations with low information or limited available time, that we're more likely to fall back on stereotypes, right? If you've just met someone, for example, someone just walked into your office for a job interview, you're more likely to fall back on potentially unconscious stereotypes than if this is someone you've known for 5 years and you know many things about them. And second, these stereotypes that you fall back on often work to the detriment of groups that are already disadvantaged. So what's the point here? Well, in a sense, you can sort of imagine that the process of simplifying an algorithm is asking it to take the rich representation of a person, and for reasons that we might be imposing for all sorts of reasonable goals, we're asking it to instead use a much more reduced representation. We're asking it essentially to fall back on the stereotype. That was the intuitive premise, right? Is the process of simplifying the representation the algorithm uses something like the formation of stereotypes, and could we see some of these same phenomena arise? Now, at that level, that seems like an extremely vague intuition, but what's interesting is that you can actually make that intuition concrete, and you can actually see that process actually happening, and that's what I want to show in this talk. I'll illustrate it within the model that we used in the paper, but then I'll show it through an extended example, and then argue that what happens in the example happens in the theorem in the paper. Okay, so first let's talk about the model that we're going to use, and think of this just as a very simple model of a screening decision, such as we might use in hiring, admissions, lending, and all these other domains I talked about. If you want, as a running example, think of it as we're engaged in PhD admissions, and we have applicants, and each applicant is described by some feature vector. Think of that as a set of, for our purposes, Boolean variables, though in the paper it's not crucial that they be Boolean. And we have a function f that describes the so-called productivity of the applicant with respect to their features. F of x is how they will do in our program if we admit them as a function of their features x. And our plan is to simply sort all the applicants by f value and admit the top r fraction for some number r. Okay. Now we're concerned about the risk of bias, and let's think about bias with respect to a partition of our applicants into two groups, the advantage group A and the disadvantage group D. So in some sense, each applicant really has this extended feature vector x comma A or x comma D. Now, crucially, the function f, the set of features x in our stylized setting, these k Boolean variables, are sufficient to completely determine the productivity. So if I know all of these features x1 to xk, I don't care about their group membership. So in some sense, f of x comma A is the same as f of x comma D, which is just f of x. Okay, to abuse notation slightly. So if that's true, if I don't care what group they come from, in what sense is there disadvantage? Well, there's disadvantage in the sense that features are distributed differently in the two groups. So if I say that mu of x comma gamma is the fraction of the population that has features x and group membership gamma, where gamma is either A or D, then we're going to imagine that there's a so-called likelihood ratio condition that applies to the feature vectors, which says that if x is a better feature vector than x prime, it confers a higher value of f, then it's more overrepresented in group A than group D. Right? So in some sense, group A, through their advantage in society, has been able to more easily acquire feature vectors that confer higher values of f. And so we should think of the decision maker in our story here as not actively biased, right? So they're not trying to engage in bias against group D, but they're also in some sense lazy, in the sense that they're not particularly concerned that group A has a better distribution of feature vectors than group D. Okay, so there's disadvantage, but there's not decision makers, actively trying to do anything to work against group D. That's already present in the distribution of feature vectors. Okay, so let me instantiate this with an extremely simple example, simple enough that we can kind of just process it in real time as I go through the talk. And again, despite being very simple, the example will turn out to contain the main issues that show up in our theorem. And then at the end, I will essentially conclude by saying that what happens in the example is happening in general. Okay, so here is the extremely simple example. Let's imagine we have two Boolean variables, x1 and x2. We have an equal number of applicants from group A and D, and the whole state of the model is given by this truth table, namely the true criterion that we're evaluating is the conjunction of x1 and x2. So they should both be equal to 1. The advantage is manifested in the fact that applicants from group A have a 2/3 probability of having each variable set equal to 1 independently. And applicants from group D only have a 1/3 probability of each variable being set to 1 independently. Okay, and that gives us the proportions here, right? So the fraction of people from group D who have both equal to 1 is 1/3 times 1/3 times 1/2, so it's 1/18. Whereas with group A, it's 2/3 times 2/3 times 1/2 and 4/18. And then we're going to sort and we're going to omit the top R fraction. Okay, So what happens in this example? Well, at all small admission rates, say r less than or equal to 5/18, the fraction of ones in the population, everybody who's admitted has an F value of 1. But the disadvantage manifests itself in the fact that only a 1/5 fraction come from group D. Okay, now this is we're trying to tell a story here about simplification. So obviously the function in my example is not in much need of simplification for any practical purpose. But again, let's imagine for purpose of the example that we decide to simplify it by collecting only x1, not both features, right? Why is that? Well, in our running example of PhD admissions, maybe x1 is a Boolean variable saying, did you have good grades or not? And x2 is a Boolean variable saying, did you do good undergrad research or not? Now, x1 is easy to collect and evaluate. We just look at a transcript. But x2 might involve having to like read somebody's paper or do some much more extensive amount of work. So maybe collecting x2 is simply too expensive. Maybe if it's a more complicated instance than this, it's because our model is too complicated and we're trying to simplify it. An intriguing reason why you might do this is for the process of regularization, right? It might be that I'm trying to improve out of sample fit by actually using a more parsimonious model. So for any of a number of reasons, I might be simplifying. And let's imagine I just project out x2. Okay, when I project out x2, then what I have is not f, but some sort of f approximator. In other words, I take a bunch of rows of the truth table, I collapse them into a single cell, and I just admit people indistinguishably from that cell, and I get the average f value, right? So if I projected out x2, I now have my 2-row truth table here, everyone with x1 equal to 1, everyone with x1 equal to 0. And I would just pull people from the first cell until I exhausted the first cell, then I pull people from the second cell. And that's how my admissions process would work. So now at all small admission rates, the average F value is 5/9, not 1. And the fraction coming from group D is 1/3, not 1/5. So relative to the true F, we have a story that is familiar from work in this area, which is we have gains in equity. I'm admitting a larger fraction from D because I removed one variable to confer disadvantage. On the other hand, I have losses in efficiency that the average productivity is lower. And so a lot of work here often thinks in terms of that trade-off. And simplifying certainly produces that trade-off. But the point in our paper is that it causes two more subtle difficulties that seem important to bring to light. Let's think of the first one as a difficulty and the second one maybe as a missed opportunity. So the first one is the following difficulty. So I said earlier that the decision maker here is not biased in particular against group D. They're just somewhat lazy and unconcerned about the fact that we're in a system where there is disadvantage against group D. They're simply looking at F, right? They're simply an F maximizer. They're not particularly concerned with the disadvantage. But in particular, if the decision maker had this truth table and they're admitting people in the full 8-row truth table, and you ask them, here's x1 and x2, would you like to know this applicant's group membership? They would say, no, I don't care about this applicant's group membership because x1, x2 tell me everything I need to know to evaluate the criteria of interest. Now we simplify it, we collapse it down, and we ask them the same question. Would you like to know this applicant's group membership? But now they say, actually, yes. In fact, I would like to know this applicant's group membership because we haven't collected x2. But if you told me the group membership, then I would convert this truth table on the right to this 4-row truth table on the left, in which I use x1 and the group membership. Because of course, the group membership is proxying, in at least through some correlation, with the variable that I'm not able to collect, right? So the point is that that simplification has transformed disadvantage into bias, into an actual active incentive to discriminate against group D that wasn't actually present before, right? And why is that? Because dropping a variable creates for an F maximizer an incentive to use the group variable in a way that actually hurts group D. And so what's interesting is that this is sort of the first indication that actually it's possible to formalize what initially seemed like this very vague intuition that by forcing an algorithm to simplify, you're asking it to engage in a stereotype, that stereotypes are particularly bad when we're in situations of low information, and that they tend to work to the detriment of people who are already disadvantaged. And all of that is happening in this extremely simple example, right? This is the basic mechanism for stereotype formation. I took away a variable that you wanted, and as a result, you now fall back on correlations that you have based on stereotypes about groups. So in that sense, it's closely connected to these behavioral models. It's connected in a slightly more distant sense to economics models of statistical discrimination. And we even see it in sort of troubling ways in public policy settings. So for example, there's been a lot of work over the past 10 years to introduce so-called beyond the box policies in hiring, where you ask employers not to, that you enjoin, that you forbid employers from asking, for example, job applicants if they have a criminal record, as part of the goal of helping returning citizens re-enter the workforce. And a number of empirical social scientists did a number of very creative audit studies to show that actually in jurisdictions that introduce beyond the box policies, right at the discontinuity introduced by that new policy, you actually find that in some troubling ways, the rate of discrimination can actually increase. Their argument being that when employers are not allowed to ask certain questions, they fall back on stereotypes in certain pernicious ways, right? This is not to say to arbitrate whether beyond the box policies are good or bad, only that they come with this two-edged nature, that if you hold back certain information from people, they tend to fall back on other forms of information that are often work in pernicious ways. And so we think of this as a very human thing, in some sense actually a very complex human behavior. But our point here is that even an 8-line truth table will do this if you withhold a variable from it and then instruct it to maximize the objective function. So that's the first problem that comes about with simplification. Right, simplification clearly has the benefits it has, but it also has this concern. The second issue that comes up is that simplification of the type that I'm describing, of dropping variables, is never even the best thing to do. It's never actually ever Pareto optimal with respect to efficiency, the value of F, and equity, the representation of group D. And what do I mean by that? So let's again go back to our 2-line truth table and try some different operation on it. Suppose that the decision maker said, what I'm going to do is, at greater expense, I'm going to collect variable x2 in a limited sense. So for members of group D, with x2 equal to 1, I'm going to record which applicants have this profile. Both variables equal to 1, they come from group D. And in that way, I'll build this 3-line truth table. I'll basically sculpt out a little piece of this first cell and make it a separate cell. And again, I'll admit from top to bottom. So I'll admit from row 1 until it's exhausted, then row 2, and then row 3. And in this way, what I've done is I've created a new F approximator by sculpting out of the cell. And I've simultaneously improved efficiency, because for every admission rate, the average value of F that I'm getting, if I admit in this order, is at least as good and sometimes strictly better, right? Because I've taken the cell and I've admitted in a slightly better order. And it's also simultaneously at least as good in equity, representation group D, and for some values of admission rates strictly better, because I'm starting by admitting from group D. Now, you could ask, this is an interesting operation on this particular truth table. Is this something that we actually do in real life? And I would argue that it is. If you think about PhD admission programs, often a PhD admissions committee might ask itself, how do we get more applicants from group D? And they say to themselves, let's run an internship program for undergrads from group D in junior year of college. They'll come, they'll work with us, they'll do undergrad research. And the ones who do particularly well at undergrad research, we will remember that for the PhD application, and we'll, and then we'll take them to count admissions. What have they done? They've basically taken this amorphous mass of people with high grades, row number 1, and they've sculpted out a cell where at some amount of expense, they're going to collect this more expensive variable for group D, and they're going to now admit using this reasoning, right? And so in some very stylized sense, that is the kind of operation that we're doing when we engage in these kinds of activities. It also suggests an interesting algorithmic question somewhere in here, which is to look for opportunities for strategic unsimplification, right? Then we have a simple rule, and in some sense, all rules are simple, right? We never collect every variable that we could. If we have a limited ability to expend additional resources, what else should we collect and how, in order to potentially achieve these Pareto improvements where we simultaneously raise efficiency and equity? So that's the picture that emerges, right? In the space of all possible simplifications of this Boolean function, of which we start with the trivial simplification, the function itself, this kind of projecting out of variables puts us at an unstable point on the landscape. In one direction, we can tilt toward incentivized bias, where decision makers seek out group membership in a way that works to the disadvantage of groups that are already disadvantaged. And in the other, we can potentially climb toward Pareto improvement, where we sculpt out pieces of certain cells to simultaneously improve efficiency and equity. And the point from our EC paper is that what happens in this example happens in general for arbitrary Boolean functions. And so essentially the theorem, slightly informally stated, is that for every Boolean function with real valued outputs that satisfies our disadvantage condition, right, that likelihood ratio condition on distribution of feature vectors, and a genericity assumption, which I won't try to spell out here, that the function is generic in a certain sense, that there aren't numerical coincidences in its values. And for every simplification G of that function, namely taking feature vectors and partitioning sets of them, right, partitioning them into cells by fixing certain variables, such as a decision tree might, for example, then two things hold for that. One is that compared to our simplification G, there is always an F approximator that strictly improves on G in both efficiency and in equity, right? So we always get this Pareto improvement. There's always, in some direction, an opportunity to strategically unsimplify that makes a Pareto improvement. And secondly, if G is an F approximator that does not use group membership, then adding group membership as a variable increases efficiency and reduces equity, right? And this is the pernicious incentive I was talking about, right? Adding group membership becomes an incentive because it increases efficiency for the decision maker. And it's pernicious because if the decision maker adds it to increase efficiency, it's going to actually reduce the representation of group G. And so the point is all F approximators for arbitrary Boolean functions are going to have this pair of properties that we've been talking about. I just wanted to say 2 slides about something about the proof, since again, the example contains these phenomena, but it's sort of so clear why it contains these phenomena, it's natural to ask, what else do we have to do to prove this in general? And it turns out there's one extra source of difficulty here that does not show up in the example. And so I'll show you a second example that makes this difficulty clear. This is now another 8-line truth table, same format. But now it's some real valued Boolean function. It's not something we're going to be able to work out in our heads. But let me tell you why I'm showing this example. This example is designed to address the question, what if we relaxed the disadvantage condition, which is currently expressed as a likelihood ratio condition on every feature vector? We relaxed it to simply a difference in means. Suppose I simply said A is advantaged in the sense that the average value of F in group A is higher than the average value of group D. Now that's certainly implied by the likelihood ratio condition, but it's a much weaker condition in the sense that the difference in means requires much less for that to hold. Okay, would that be enough for my theorem to hold? And the answer is no. And the reason why not is instructive, and it shows what the proof has to do to make use of the likelihood ratio condition. So here's a counterexample to a difference in means implying the conclusions of our theorem. I take this truth table, which again, we can't quite work this out in our head, but let me show you what this particular simplification of it does. I drop out x2 and I get this 4-line truth table, the value of x1, the value of group membership. And although D has the lower average, a funny thing happens, which is that for the subset of the population where x1 is equal to 1, conditional on that, group D has a higher average. Similarly, for the subset of the population where x1 is equal to 0, group D also has a higher average. So a decision maker here who only had access to x1 would have an incentive to seek out the group membership variable, but it would be so as to discriminate in favor of group D, the disadvantaged group that has the lower average value of F. Because no matter what the value of x1 is, D will do better. Now you could ask yourself, how can it be that the average for D is lower, and yet conditional on any possible realization of x1, the average for D is higher? But that, of course, is Simpson's paradox, which obviously is very familiar to this audience. So in a sense, what this example is showing is that the mean in group A exceeds the mean in group D, but the F approximator using only x1 and gamma can't be Pareto improved. And the incentive it has is actually to use it in a way that favors group D. And so the crux of what we're doing is essentially, in order to prove this, we have to prove a kind of anti-Simpson result, that with the likelihood ratio condition, the analog of Simpson's paradox in our setting can't happen. And so basically the sort of combinatorial lemma that we have to prove is, again, rewriting the likelihood ratio condition here, is that for any non-trivial partition for an arbitrary function now. For any non-trivial partition of the feature vector for A into cells and for D into cells. And if we give each extended feature vector a value equal to the measure weighted average of F in its cell, there exists at least one feature vector for which group A is strictly doing better than group D in the approximation. And that one feature vector that you can show the existence of can't happen in Simpson's paradox, but likelihood ratio smooths that out. It gives us sort of the handhold that we need to then create the proto improvement, to create the pernicious incentive for an arbitrary Boolean function. And with that, I wanted to wrap up. So we have these two observations about the process of simplifying complex functions when they're being used for evaluating individuals. I think there are a lot of interesting questions here. One is somehow just this idea of the space of all simplifications of F and sort of walking around in that landscape, keeping track of efficiency and equity as two metrics of interest. A second is that our notion of simplification is well suited to basically taking the hypercube of values and breaking it into subcubes. But there are other more syntactic notions of simplification. For example, a linear functional form is a simplification. It uses all the variables, but it constrains itself in some other way. And it's interesting to ask to what extent some of these theorems can hold there as well. Again, it's intriguing that one big reason why people use simplification has nothing to do with human cognitive complexity, but is rather about regularization for purpose of out-of-sample generalization. And so there's some interesting question here, which is there some fundamental tension between regularization and fairness for exactly these reasons? That essentially, when you regularize an algorithm, you're explicitly asking it to engage in stereotyping, right? And it's using stereotyping to generalize to out-of-sample, but it may run into all of these problems. And finally, of course, this has all been a story about selecting individuals, whereas in fact, in many of my stories, if I'm hiring a team, I'm admitting and entering class, I'm really selecting a group. And so in some sense, it's interesting to ask all these questions when the objective is actually a set function over all the individuals that I choose, not just one at a time. And so more broadly, what's been interesting here is this convergence of ideas from theoretical computer science, from the behavioral sciences, and from public policy, I think suggests that there are a lot of interesting questions to be explored, and one in which the style of work that we see at this conference, I think, of course, stands to play an extremely central role. Thanks very much.